bit spicy. We're going to go deep dive on a few different topics here. But in my opinion, verifiable compute is going to eat the world, and it is already kind of doing this today. So normally when like a new trend comes out, there's different cycles of it. One is like we all hear about it for specific use cases, and then eventually it becomes just like everywhere, ubiquitous. But first, like a very early stage, it's mostly like technical people. Like when the internet came out, I'm sure it was just very technical people. And then in the very end, we all end up using it. And with many other technologies, it's kind of the same trend where it's techies, normal people, and then it's just working in the background without anyone really knowing that's even there. I'm the technical founder of a project called NovaNet. We use something called folding schemes to do both privacy and local verifiable compute for ZKP. So what are blockchains even good for in the first place? They're very good for being a decentralized source of truth. So anyone can check on the blockchain to make sure that they have the correct balances and things like this. And this is why we saw DeFi as kind of the first core use cases for blockchains more generally. They're also tamper-proof and secure. So you can, if you have a balance on there, you know that it's there and no one can come in and mess with it and tweak it. Or the government can't also come in and mess with your balances. They're also immutable, which means no one can change them. But the really bad things about them is like you have to re-execute. There's a lot of computational work that goes into making blockchains secure. Bitcoin is notorious for being extremely expensive in terms of electricity, like literal power. So there's this whole consensus that goes into them that's extraordinarily expensive. They're completely transparent. So if I give you my ETH address or my base ID, base name, whatever we're calling it, and you get that, you can see everything I've ever done on the blockchain. You can see all my NFTs, you can see basically anything that's ever occurred there. And that's obviously a huge limiting factor for a lot of individuals and also corporations and regular people and basically everyone who's trying to use blockchains for these use cases. So for anything really, I would say that needs privacy, regular blockchains just don't work. And then there's like a huge battle constantly in the blockchain space over scaling. Like there's basically everyone's like, hey, we have the fastest blockchains. But scaling's always been a big issue with blockchains more generally. ZKPs have basically blown up the scalability argument. There's so many L2s and rollups here that say, hey, now we have ZKP, we can have really fast, scalable blockchains. And the entire ETH roadmap has been changed to add in ZKVMs now as a kind of a core component because you can run many of these and have very succinct proofs. And by succinct, I mean it's very cheap to check that the proofs are correct. It might be expensive to create them, but you can basically check them in a few seconds or less. This narrative has been very driven by Starks, which is this kind of monolithic type proving scheme that's very fast, but it's also kind of expensive. They have larger proof sizes, and it's based on like hashes. So I think, like we mentioned this a little bit earlier in one of the talks, like it really does disrupt the more general Web3 space. If I can run something locally and prove it to anyone, why would I even like need to use a blockchain? Like we can literally just do these computations and say, hey, I played this game correctly, or hey, we did this one thing, just verify the proof directly. So we have trust without transparency, which is very cool with things like ZKP2P. Like there's a project out there that you actually have funds and you say, hey, I sent these funds in a private way, you can pick up the balance here. It's extremely efficient for scaling, and you can actually have more complex smart contracts than you do on current blockchains because you can verify quicker. So before, there's something called gas that restrains you on basically what computations you can do on a blockchain, but now you can do the computation off-chain and just verify on-chain. So this is once again, important from the succinctness standpoint. I can do some super crazy computation that would be so expensive to do on L1 that you just wouldn't be able to do it. Now I can do this off-chain and just host this really tiny proof on-chain that anyone can check. So really, like I see it as a third dimension for blockchains. We had Bitcoin, which is kind of like a straight line. We had a second dimension, which is programmable contracts with Ethereum, and now we have this third verifiable compute space that's essentially saying, hey, any computation in the world, you can just verify on a blockchain. So what should the blockchains even do in this new world? They are still a source of truth for orchestration, like who owes what if you're having an account balance and things like that. They're definitely going to be a verification layer. This is for rollups or anything else. If you have a verifier on chain, that's where the source of truth would be. And also, another important thing, there was a paper recently that talked about this too. You potentially just have a DA layer with a ZKP layer, and the data is coming from this like trusted data layer. And that's just, I think it's interesting that you can potentially just have the blockchain hosting the data. I wrote this in Japanese because I'm going to redo this in Japan. I lived in Japan for a while, so it's just basically saying, oh, ZK is the future. But the current mindset, even among technical people, is, hey, ZK is awesome, but it's still way too slow for anything I really want to do with it. But this is changing very, very quickly. So this is just from like public information. Anyone can go on these people's websites and verify like how large these ZKPs that exist are today and what type of machines you need to run them. So one good example is like SB1, and on their site it says they need a minimum of 128 gigabytes to run on their ZKVM. This means essentially you're going to need a special computer to run the ZKVM. So hey guys, you used to like code custom circuits, do all this other stuff, but here's this cool ZKVM that you can use directly out of the box. But guess what? You need a special machine. Like you're not going to be able to run it on your Mac. And this is true with like Jolt and Restio. Like it's very centralizing in the sense that you can't even try to like experiment with it unless you like rent an AWS machine. Restio is actually on the better side. That's 12 gigabytes. Some Macs and some regular computers can do that. Jolt is, from their docs, is still at 80 gigabytes. But on the other end of the spectrum, we have folding schemes, which are cool because you can choose the step size and you can make things tiny if you want to. So this stuff you can just try out. Like you'll see, oh, it's doing about 200 megabytes of memory, and this is making it extremely portable. The trade-off here, obviously, is like SB1 is going to be super fast. It's a special machine that's going full power. So you do have a little bit of loss in speed, but depending on your problem set, you don't need, like if you're not proving a whole block of Ethereum, or if you're not doing like some crazy computation, you can just use something smaller. And that's true for a lot of different types of applications, like privacy preserving ones. So one great and kind of notorious example is like Tornado Cache, which was like illegal, and now they kind of cleared that. But that was running like years ago directly in your browser. So like ZKP being slow and big is kind of a narrative that's focused more on scaling blockchains rather than the privacy aspect, where we can actually run a lot of stuff directly, and we have been for a while in browsers. So what is a folding scheme? This is like the tech I love to show because there's so much narrative around like Starks and Fries and stuff like that. It was actually, the original paper was KSC 22, is the Nova paper, and there's a whole line of works after that. There's like basically every month someone is publishing something new on this topic of a folding scheme. But basically what it lets you do is very good continuations and very good recursion. So before, basically what you have to do is take a snark, which is mathematics, and put another one inside of it. So it's like math on top of math on top of math, which is like extremely expensive to do. But with folding scheme, you just don't have this math. Like you skip the snark, and you have a more efficient way of having the mathematics. So it's literally like no snark, no snark. And the very end is when you're actually doing like this full ZKP math. And with this, you have the best recursion overhead in the literature, which means you can do something called incremental verifiable computation. So I was talking about monolithic provers earlier, where if you start a problem and it's big, like if you need it to all kind of fit in this prover's head, and if the prover dies midway, you have to like restart from the beginning. But with this incremental verifiable computation, you actually stop, go. Like I can start a proof, you can verify it, and I can actually pass the proof on. So like you can stop, go anyway, and actually kind of piecemeal the proof. So this lets you choose a step size to match your machine, essentially, or match even like if you're cooperating with other provers. Someone might have a very large machine, someone might have a small machine, you kind of work together in a collaborative way. So this is what IBC is, and I think it's also a game changer. The original paper is by Valiant in 2008, and then all of a sudden in 2022 we had this breakthrough work on folding scheme. There's also something called non-incremental verifiable computation, and this is important for if you want to essentially have opcodes in your system that you don't want to pay for. So a good example of this is like with WASM, you might have 128 opcodes, and you don't want to pay for all those at each step. You only pay for the things that you're using. So it's just more performative in the sense that you're only paying for what you're using for. So what can we do with this technology? There's two things. One is bottom-up proving, which is privacy proofs. We might be 10,000 gamers or everyone in this room making our own proofs on our own devices. We're going to aggregate those and then post to an L1 efficiently. If we all did this individually, it would be very expensive. But the other use case is kind of this parallelization, which is cool because you can break up a big problem among many people and kind of collaborate. Prover networks, more generally, people think of like them as competitive. There's a concept of proof racing, where basically like the fastest prover wins. But really, you can get better speed if people collaborate in some settings. And this proof of cooperation allows you to do collaborative game theory with like Shapley values, so there's other cool traits about it as well. One of the cool things I like to always mention about folding schemes and privacy is there's a paper called the Hypernova paper, and there's a trick in it that just lets you do this one really simple thing, and then you have privacy, like just from this one trick. All ZKVMs, or the vast majority of them, they're not zero knowledge, which means they don't have privacy at all. So you're using the ZKVM thinking it's private because you use ZKVM, it's not privacy preserving. It's because they're targeted for scaling Ethereum, which is like an honorable endeavor all toward unto itself. But with folding, we actually just fold back in ZKVM. So I mentioned Jolt a little bit earlier, which is from the A16Z team. It's also focused on scaling Ethereum. It's really, really cool because you use lookups, it's really, really fast. But they still don't have privacy. Like they would have to rewrite the paper to make it private. But now with folding, we can potentially take them as a special opcode and then fold it once, and then it does get privacy in the end. So folding helps out a lot in these type of use cases where you do actually want privacy. So with this, like ZKP is actually going into the Web 2 space as well. There's been a few different companies kind of posting about how they're using ZK more recently. I think all like private preserving technologies are actually becoming more and more relevant even in Web 2. This is from Google. They have a metadata for private proof API. So they're using ZKPs directly. We can look this up later. It's kind of small on the screen. But it uses ZKP as a way to like identify and signal if an output or anti-fraud mechanism, essentially. Like I can't read either because it's all blurry. But it's basically just doing anti-fraud with ZKPs directly in the browser. So you do get these types of really cool use cases coming up and becoming more public recently. But we can do proof of location, proof of fraud protection, verifiable AI, like ZK credentials, which we talked about quite a lot today. So it's not just Web3. ZK is like very relevant to Web2, and this might be a good idea for some people in the audience or listeners. If you can do a Web2 ZK startup too. Like that's an underrepresented space. Like everyone's focused on Web3. You actually might be able to make a company easier doing like a Web2 startup using ZK. One that I like a lot is this miniaturization of models and also of ZK. Like we talked about folding scheme and it becoming smaller. Models themselves are also becoming smaller as well. There's tons of tech and money going into being able to run AI essentially on your devices. And with these smaller models, ZK becomes more easy to use, essentially. Like for regular LLMs, these are gigantic things, and obviously ZK is like going to be a huge overhead on top of that. But with other types of models, we're actually using these today. Like there's already projects out there that are using ML for prediction in real DeFi protocols that already exist. So if you hear someone say like ZK ML is impossible, that's actually completely wrong. It just depends on what problem you're looking at. If you're looking at like prediction model, you can do it today. And if you're looking at doing stuff that's on your local device that already runs, you can probably already do it today as well. So example like gradient boosting, regression, biometrics, these types of problem sets are actually already possible. For like a huge LLM, I would say it's gonna take, I think the best time I've seen racing was like 10 minutes, and obviously no one's gonna wait around for like the robot to say one word every 10 minutes. So, but there is good tech going here and a lot of progress, basically weekly. So if we start running these models where like there might be a big company that has a model and we have some stuff locally on our devices, like how do these things interact and trust one another? Like how are we ever going to have one agent talk to another agent and the agents themselves actually can trust that the other agent wasn't swapped out or didn't have faulty data or wasn't hacked? Because essentially what you're going to have is a chain of models running. And if you have an attacker looking at that model, they're going to say, where's the weakest link in this chain? Like that's the place I'm going to go, and especially if it's doing something very serious, like they're like transferring money or like making a prediction. Is this person have like a good credit score, or are they able to get this loan? Like an attacker could potentially go in and attack the weakest link, and this is where you really want verifiability from a cryptographic sense, and that's a good spot for ZK and these other private preserving technologies. A lot of people are like in the Web3 space right now talking about TEs quite a lot for this use case because it's a hardware-based way of dealing with it. But most of us don't have $30,000 to have like a TE like running in our house. Therefore, I think it's cool for the use cases they want to use for, but I don't think it's really future-proof in the sense that like we're all gonna have keys in our pockets, but who knows? But even then, like you have to trust in the hardware, right? Like let's say they figure out this way to make keys like really cool on phones and stuff like this. If someone like a state actor goes in and messes with the hardware companies and they leak or basically have side channel attacks, you can be trusting the system for something that's not even like trustworthy. That's why I think math and ZKP, this like type of cryptography is much more secure than TEs in the long run. There's other processes like custom consensus mechanisms that do this. These are interesting for like decentralized training of AI. I'm not going to go too deep in those. FHE is another cool technology, fully homomorphic encryption, that is actually already used in production as well. And this is for like privacy preserving AI calculations. But I think really the best way is like if you just want to trust yourself on your device, the clear way going forward is on device ZK. Mentioned this earlier as well, private weights, private data, private models. These are the three core areas that, or things you can do basically with ZK/ML, or zero knowledge machine learning. Private weights are important if you're spending a ton of money and you actually don't want to give the weights in public, but you do want to prove that you're running this model correctly. Private data, I can have really good stock data, or really good, like I can make a prediction of Bitcoin next week and always be accurate. If I had that data, I wouldn't want to give that away. Like I wouldn't want you to pay me for it. Like obviously, like here, it's going to be like $10 next week. Here's my model, I ran it. So there's really good reasons to have like private data, even personal data. Like it might be my emails or my private correspondence. I don't want to give that away either. And the last thing is if you create a new model. Like right now, we're basically open sourcing most of these models, but you can imagine making like a specialized model that you use that you wouldn't really want to expose to the world just yet. So you can have private models as well. Biggest complaint is it's like super slow still. ZK is way too slow. But it's made much quicker. Like there's already been orders of magnitude just in the last couple months in terms of what we're able to do here. So if we're gonna get real-time proving for blockchains, we're obviously also gonna get pretty good proving for ZKML in the longer term. I think a lot of the ZKVMs that exist today will actually be reformatted a little bit for these other type of use cases as well. If you don't care about privacy at all, you actually just give this, you can just delegate this to another party. So like a prover network or something like that. I would say actually verifiable compute is necessary for this world that we're going into. Biometrics, you definitely need privacy around any of that. For specialist models that run on your own device, you would want them to have, once again, verifiability. And also to prove the models that you said that you ran, basically. This is actually a quote from 2001 from a famous AI researcher called Rich Sutton. An AI system can create and maintain only the knowledge to the extent that it can verify that knowledge itself. This is basically going back to the fact that like, if you have an AI, how do you know it's not just bullshitting you and just making stuff up? And the old way to do this is to say, hey, we get a human to come and verify that it actually has facts and real knowledge. Going into the future, like this could be done with cryptography. Rather than having a human come in and verify every time, we can say, hey, we know for a fact that this AI was trained on information that came from real doctors or like a real professional. So these AI to AI can actually verify once again. So this famous quote, I think, actually changes in 2025 to be verifiable computation, essentially. An AI system can only truly create and maintain knowledge to the extent that it can verify that knowledge on its own, which you can do with ZKP, succinctly and reliably. This is a fun one for our Web 2 people. If you never hold the data, you're not responsible for it. So if you're a company and you have to you have this area where like, hey, I have to collect this private data for this one thing, like checking if someone's above the age of 18 or seeing if they're in New York or seeing where they are. If you never hold the data, you're not responsible. So like using ZK in the Web 2 space, once again, like if you just had these proofs running locally, verifying things and you don't actually need to ever like store people's personal data, it's less risky for you as a company. Anything that stores data becomes a honeypot. Like hackers will come and look for any way to break it. And I'm always amazed how like people kind of just look this over like, oh, no, it's fine, like this is secure enough. Most systems are breakable. Like they're going to get broken. And if you have to store this stuff in a honeypot, you probably just don't want to do that in the first place. And this is not just about like decentralization or some like strange philosophy. It's just like a fact. Like, don't make the honeypot in the first place. So more generally, in every aspect, we might not see it from being regular consumers, but I do believe that variable compute is eating the world. It's more in the background for now, but just like the internet and other technologies, it starts off with people who are interested and then becomes mainstream, and people don't even realize it. Oh, there's a phone, this is very, or like, yeah. And then it becomes mainstream, and we all just have phones running in our pockets, essentially. NovaNet has been around for around 2 years now. The code is always open source, so you can actually go check at devs.novanet.xyz for the open source docs. There's a ZK WASM implementation that runs directly in browsers, so you can basically take any computation and run it through the ZK WASM. My technical blog is very focused on like CTO types, so it's like technical to technical people. You can basically check the entire history of the company there and where it's going in the future. We actually, we're on Twitter and we're on other social media. There's something fun that we can all try right now. It's called zkp.fun, and this lets you try out this technology like in your browser. You press a button and it works. There's 2 parties. It's called proof parties. There's 2 parties out there right now. They're pretty good. We're going to add more and more parties about some of the examples I showed today, like the ZKML and stuff like that. And this will be basically consumer facing, where you go and say, I'm going to press the button and I want to see how long it takes. One cool example that we're probably going to push around next week is just ZK ECDSA, which is the way to say, hey, I own this NFT, but I'm not going to dox myself. I'm not going to give you my Ethereum address. So it's like privacy preserving NFT stuff. Or like base name, like I have a base name, or I have this, I have a base name. I don't want to give you my exact base name. So it's used for that type of technology, but there's a few interesting things that you could definitely check out on zkp.fun. But yeah, unless there's questions, that's basically all I had.
You talked about like verifying the outputs of AI, like the small language models. I don't like understand how you can verify it using ZK, because like let's say like it communicates to a network, right? Like what if you just like split the network? Like I don't understand how you can like verify the entire process of like the language model running without like if someone like attacks it.
So what I'm talking about is models that are running on your own machine, right? So we're not talking about a network layer that always is running on your own device. Sorry. And with this, like what happens is you would be trusting yourself essentially. You know that you're running the model correctly. And with ZKP, what happens is the computation is a part of the algorithm. So anyone can see normally the model or whatever the algorithm is, and this is what you use to generate the public parameters. What you're saying is with these inputs, I know for a fact that you ran it correctly on your own device. So if you're in a server setting, you're basically saying, I'm the big server, I'm running it through. You also know what computation I'm running, and you can check, like double check the facts. And here's the proof that shows you that I ran it correctly. So normally, like the model, like the computation itself is actually inside the R1CS or inside the constraints. So that's just like public knowledge, and that's what you're verifying against. I don't think the network layer is actually an issue there whatsoever, unless you're like taking like data from a third party and maybe using that for your ZK. But if you're running everything locally, that's like the best way to make sure, like for yourself, to make sure it's run correctly.
Thank you.
Go for it.
I'm kind of curious. So, like for NovaNet, since you're a folding-based like ZKP, right? What kind of folding schemes are you using right now in production?
Yeah.
How are you making the proofs of state?
Yeah, that's actually a really good and on-point question. We're the first team that implemented something called Supernova. So Microsoft is the main. They made the KST22 paper, and they did the first Nova repo, and they still, like, it's open source and anyone can contribute to that. We did the first Supernova implementation. We like that because it's NIVC, which we can talk about a different time. Yeah, so we went from that, and then we went to Nebulize, our most recent form. So we're basically following like this work from the Microsoft team and implementing as they go. And it used to take a lot of work, and it gets smaller and smaller as we go. So the first implementation was Nova, which had like 2 MSMs, which is like kind of heavy. Now it only takes 1 MSM, and you're only committing to something called the witness. So it's like becoming very refined in terms of like how fast these folding schemes are gonna be. And now with one MSM, we're only committing to the witness, like it's 10x of what we had originally. So like this is getting better and better and better. I think people were very focused on like Fry type systems for using smaller fields, but it turns out you can actually use smaller fields with Nova too, as long as you like, if you use lattices. So there's other ways to get these kind of cool traits that people have found in other spaces. With the end proof, what you have actually is Spartan is the end wrapper here, right? And with Spartan, you're basically taking this large proof and making it smaller. But what you can do with this is actually have this delegated prover type model where you keep the witness private and you run 10% of the computation and you export 90% away. So you can have both kind of like small on-device proving and then also compression somewhere as well. So there's been a few cool tricks under that area.
That's cool.
Yeah.
So you mentioned how NovaNet is a lot smaller compared to Jolt and RISC-0. What are the trade-offs if that's the case? Assuming there's no free lunch, or you can tell me there is in fact free lunch.
No, there's no free lunch. Speed is a big trade-off there. You're basically choosing to make memory trade for speed. But here's the thing: is like if you're doing, you can basically use Jolt in folding 2. So if we use Jolt as a specialized circuit in our stuff, we would have like, for the space bound, we'd have a lot of speed. So if we only have 8 gigabytes, we can use all of that, and then just fold these Jolt proofs together. So you're basically trading off these two things. So it's depending on like what your problem is. Like if you really want real-time proving for Ethereum, you're gonna want, it doesn't matter how much, you're gonna want 1 million machines running as fast as possible, just get it done with under 12 seconds. But if that's not your use case, like privacy is your use case, like you can't use the other stuff, you're gonna want it to be a little bit smaller, and you might have to wait 10, 20 more seconds depending on the use case, right? But like I mentioned earlier, like Tornado Cache was a very early example of doing it directly in your browser. And I think you had to wait like a minute or two. And so it was already possible like years ago. Like we already had this technology. It just wasn't easy enough for people to really like use, and it wasn't like great UI, right? That's another huge issue, is if you have random people coming in and they're trying to use it, you want the UI to be good. So there's a few ways people are dealing with. One is like you just show the result and then have the proof verify a little bit later. Or you have fast proving locally, and that's where we like optimize constantly. I would say the next step for us is doing something called Neutron Nova, which will give us another 10x. And then we'll have web GPU, which will give us like, right, so far it's like 8x. So that's just like 2 things we're doing super short term that is just like, if it took you a minute, now it's gonna take like 8 seconds, which is crazy.
Have you looked into, proof delegation in a price-preserving way?
Yeah, we already have actually open source delegated Spartan. It's actually in the same, if anyone wants to look in like the ICME GitHub. And that's what the trick I was talking about earlier, where you can basically take this proving scheme called Spartan. The witness or the privacy preserving part is done locally. And this is like 1, or I would say 10% of the whole computation. You take the sparse polynomial evaluations, which is the big part, and you just send that to whomever. Like it's not, you don't really care about privacy anymore, but you already use the private part. So the untrusted prover can just be given this data and they can run as fast as possible. And this is where you might have a prover network or a big machine running in the background, compressing these proofs and posting on chain. And that's not just us. I think it's been trending a little bit recently. I think WorldCoin is doing one as well with like Whir and Spartan. But it's these holographic snarks, like Marlin, Spartan, et cetera, where you're able to do this. The issue with this still is like you're kind of constrained by the problem size, right? If the first part is still too big for your device, you're still screwed. Like, it's, you're not gonna be able to delegate something away that's still gonna take gigabytes and gigabytes of memory to run. So there's still a constrained problem space. But I think it's a really cool trick for a lot of problems. Thanks.